Rans-based Eulerian-Lagrangian models are a category of CFD models to simulate turbulent particle-laden flows, which combine the Eulerian-Lagrangian approach to describe the motion of the two phases with the Rans-like approach to describe turbulence in the carrier fluid. The Eulerian-Lagrangian approach relies on the Eulerian cell-based representation of the flow of the fluid phase through the numerical solution of the mass and momentum conservation equations, whereas the movement of the solid phase is reproduced by solving the Lagrangian equation of motion for a certain number of computational particles. The Rans approach means that only the largest scale of turbulence, that is, the integral scale, is resolved. All the other scales are instead modeled. The Rans approach is based on the solution of the Reynolds equations, which are obtained by applying to the Navier-Stokes equations the Reynolds averaging operator. The Reynolds average of a given fluid dynamic variable small psi, which varies in time t and space r, is referred to as capital psi, and it is defined as the limit for t infinite of 1 over t of the integral from 0 to t of small psi, function of xi, and r in xi. The meaning of the Reynolds average is as follows. Imagine focusing on the time evolution of small psi, which might represent, for instance, the pressure, in a fixed point r of the flow domain. If the flow is turbulent, the behavior of a small psi will be very chaotic and noisy. Capital psi represents the average of such noisy signal over a very long time period. Consequently, capital psi does not depend on t, but only on r. The difference between the time-varying small psi and capital psi is still a time-dependent variable, which is called fluctuating psi, and it is referred to as psi prime. From a mathematical point of view, this corresponds to the so-called Reynolds decomposition of small psi, that is, small psi, function of t and r, equal to capital psi, function of r, plus psi prime, function of t and r. By applying to the Navier-Stokes equations the Reynolds averaging operator, the Reynolds average Navier-Stokes equations, or Rans, are obtained. The Rans solved for the Reynolds average fluid dynamic variables, and for incompressible flow, their formulation is as follows. Mass conservation, nabla dot capital U equal to 0, momentum conservation, nabla dot ρf capital U equal to ρf times the gravitational acceleration vector g minus the gradient of capital P plus the dynamic viscosity μf times the Laplacian of capital U plus nabla dot the Reynolds stress tensor T-Re. The Reynolds stress tensor is associated to the double correlations of the fluctuating velocity components, and it accounts for the effect of the smallest scales of turbulence on the mean flow. Since the unknowns of the Rans should be only the Reynolds average flow parameters, which are capital P and capital U, T-Re is modeled via additional equations called turbulence model. If we compare the Navier-Stokes equations with the Rans, we note that they are formally similar, except for the following differences. First, the unknowns of the Navier-Stokes equations are the instantaneous pressure, small p, and the instantaneous velocity, small u, whereas those of the Rans are the corresponding Reynolds average quantities, capital P and capital U. Second, the Rans include the Reynolds stress tensor, which has to be modeled via a turbulence model. Third, the Rans do not include the time derivative term. Therefore, the Rans are steady-state in nature. Actually, it is a common practice to employ an extended version of the Rans called U-Rans, or unsteady Rans. This is derived by applying to the Navier-Stokes equations an averaging operator which is different than the Reynolds averaging previously defined. The U-Rans allow simulating flow processes which are unsteady at the integral scale, filtering the noise caused by the small turbulence scales. As a final note, the Rans, or the U-Rans, allow solving the flow at the integral scale of turbulence. All other scales are not resolved, but accounted for indirectly via the turbulence model. The required size of the computational mesh is governed by the integral scale, which, broadly speaking, is of the same order of magnitude of the macroscopic flow domain. The relative coarse meshes required by RANS-based models bring about a low computational burden even for complex flows, contributing to explain why RANS is the most widely used approach in engineering.